So before we leave this topic, I want to show you what I consider to be two interesting shapes. These are the shapes that really sort of force you to take what you already know about circles and rectangles and try to impose them onto this kind of competing coordinate system of polar coordinates. Um, so, if at the beginning of the course I said use integrals to find the area of the yellow rectangle on the left, you would think, wow, this is a really easy course. So let's see if we can do it in polar coordinates. The thing to understand is that this yellow rectangle, let's focus on the left figure first, and then we'll get to the one on the right. So this yellow rectangle is really going to be the area between two curves in the sense that if I draw, let's say that I draw a blue line out going that way, we can see as we intersect this curve on the left first, and then we intersect this curve on the right. So it really is understanding that a vertical line can be a polar curve. This yellow rectangle is really the area between those two polar curves, but that's not quite the full story. It's also the case that once I get up to this point here, which I'm drawing by this red line, now it changes to a different pair of polar curves. If I instead now draw a blue line like that, I intersect once again this vertical line on the left, but then I intersect the horizontal line on the top. So I really have to break this up into two integrals. So let's do the lower part first. The area is going to be, first we're going to do the lower integral. We'll put in the limits of integration. That'll be the last thing that we do actually. So it's going to be 1/2 times the integral of, I need the equations for these two vertical lines. In other words, focus again on this blue dotted line that I drew through the yellow region, showing that the inner curve is going to be the vertical line x equals 1, and the outer curve is going to be the vertical line x equals the square root of 3. We know that we can write vertical lines in polar coordinates like this. This is going to be r equals secant theta, and this is going to be r equals root 3 secant theta. So this is going to be the integral of the outer curve. Root 3 secant theta squared is just going to give us 3 secant squared theta, and then we square the secant, and that gives us secant squared theta. So just to be clear, this is going to be outer squared, and this is going to be inner squared like that. Okay. Oh, and I need a d theta at the end of that. Okay. Now, however, I need to add to that what goes on above this red line here. So we're going to put in another integral plus 1/2 integral from, and again, don't worry, I'll put in the limits of integration a bit later, integral from, didn't mean to use that color scheme, but let's keep it. The outer curve is this horizontal line. So y equals 1 is just going to be the horizontal line that we write it in polar coordinates as r equals cosecant theta. I put up a table earlier explaining how to convert horizontal and vertical lines into polar coordinates, so you can refer to that. So this is going to be, the outer function is cosecant, so that's going to be cosecant squared theta minus secant squared theta d theta. Okay, so once again, this is now outer squared, and this is inner squared. Okay, so let's all right, let's figure out what the limits of integration are. First, we can see that the starting point is going to be this line here. The horizontal line is kind of the lowest angle in which we encounter any portion of the yellow region. So I can put in 0 as the bottom limit of integration. For this line here, what I can see is that this point is going to be the point root 3 comma 1. So when we use the slope formula with the point 0, 0 here, we're going to see that the slope of that line is 1 over root 3. We know that for a line that passes through the origin, the polar equation for it is theta equals whatever angle has a tangent of that slope. In other words, we're looking for an angle where, theta, we're looking for an angle theta such that tangent of theta is equal to the slope of the line. The slope of the line is 1 over root 3. The angle whose tangent is 1 over root 3 is pi over 6. So this is going to go from 0 up to pi over 6. Now, we need to do the same thing to find out where we stop integrating. I can put in actually pi over 6 down here because once I finish the first integral, I'm going to pick up where I left off to do the top half of this yellow region. I just need to know what the angle is that tells me where to stop. This point here is the point 1, 1. So we can see that there's going to be a line whose slope is 1. We already know that the pure diagonal line, y equals x, which would pass through 0, 0, and 1, 1, we already know that that's theta equals pi over 4. We've covered that from in previous examples. So this is going to be up to pi over 4. So that's the answer. That's how you would do. That's how you would integrate this to find the area of this rectangle in polar coordinates. It's kind of interesting how something that looks that simple in rectangular coordinates becomes this complicated in polar coordinates. But it's working this type of example that really gives you the intuition that you need to do polar coordinates. I will tell you that when you get to Calc 3, if you're taking Calc 3, basically an enormous amount of the course is done in polar coordinates, and a lot of your ability to succeed is based on your ability to see these kinds of shapes, very basic shapes, lines, circles, to see what they come out to in polar coordinates. So it's worth acquiring this skill now. Now let's look at the problem on the right. Let's see, draw a line there so we can separate it. So this is actually, in some ways, this is more complicated. In some ways, it's easier. But let's draw a line through here so we can see what the inner and outer curves are. We can easily see, just by drawing this radial line, based on the fact that we first intersect the blue curve and then we intersect the purple curve, that the purple curve is the outside curve and the blue curve is the inside curve. So what's the blue curve? It appears to be just a vertical line passing through 1/2. So I'll draw it down here. So that's just going to be r equals 1/2 secant theta. We know that's how we write a vertical line in polar coordinates. So what we're looking for is to integrate. Let's see what we can figure out. It looks like the bottom of the curve is still going to be theta equals 0, and the top of the curve is going to be some angle we're going to have to solve for. And it does not look as if the inner and outer curves are going to change. Notice that in the left example, the inner and outer curves actually changed midway through the example. In the example you see on the right, that doesn't happen. In the example you see on the right, the curves do not change. So fortunately, we're only going to have to find one point of intersection. Let's find that point of intersection by setting the two curves equal to each other. We have this curve and we have this curve. So we're going to set 1 equal to 1/2 secant theta. That gives us 2 equals secant theta, or theta is equal to pi. Well, let me do it this way. If secant theta is 2, then that means that cosine theta is 1/2, right? Because secant is just the reciprocal of cosine, so that gives us theta equals pi over 3. So that means that this line here is theta equals pi over 3. This one is theta equals 0, so that gives us our limits of integration. Let's find the area. It's going to be 1/2 times the integral from 0 to pi over 3 of, we've got the outer function, which is just a circle of radius 1, so that's going to be 1 squared, minus 1/2 secant theta squared d theta. If we want to write this a little bit more cleanly, that comes out to integral from 0 to pi over 3 of 1 minus 1/4 secant squared theta d theta. There's the answer. So turns out the left shape is probably a little more complicated than the right shape. Maybe I should have done that one first, but these are both just interesting shapes that I think, just force you to think about how these shapes work in polar coordinates, and it's worth going through both examples for that reason. So there we go. That's how polar coordinates works.